All right, there we go. Good morning. Good to see you guys. Happy Wednesday. Is that right? Crazy. Hopefully you have something out that looks like this. I made a lot of copies of these and I put them downstairs so you can stop by later today if you don't have one or if you need extra copies, you can do that. I also dropped a link to this website, PDFs of this. So if you wanted to make your own, that's fine. Or you can hand draw them yourself. That's up to you. It's just much easier if you have the graphs in front of you. A couple other things that I think would be really, really nice to have so that you don't have to go searching for a lot of these answers would have I'd probably take out like a unit circle. Maybe a calculator would be good to have so that you can mess around with some of these graphs really quickly. I can also show you around the calculator a little bit today so that we can graph these really quickly and really easily, but also show you some of the things that might get screwed up in the calculator should you run into some of those problems. I can give you some ideas on how to troubleshoot those. When it comes time to actually graph these, calculators can be really helpful. But a lot of times what classes will do with these kind of things is we won't actually, when it comes time to test, I guess, we won't actually do a ton of graphing. We'll graph a little bit, but we'll want to understand what the equations are telling us about what the graphs are going to look like without actually looking at the graphs. So let's do it. I would probably also, for not right this very moment, but in the very near future today, have a couple colored somethings, colored pencils, colored markers, colored pens or something. Because although I made, I think, like 40 copies of this graph, we're still going to want to reduce how many we're using and reuse them as we mess around with different changes in the graphs that we make once we start messing with them. But we're just going to do some simple ones just to start, and we're just going to do one at a time. And so to do that, I would turn, if you did come get my copies, just turn to the first one, number one, on page one. I tried to number both the pages and the graphs so that we could try to stay consistent, so that if we bounce around a little bit, at least we all have the same looking stuff. That's what I'm hoping for. And I just want to do sine first. I want to look at the graph of like y equals sine of theta. And you can call it y equals, obviously, if we wanted to, and hey, why not? We could call it like f of theta, a function of theta, because that's going to be our input. The angles, you can see, are listed there in radians along the x-axis, and it really even shouldn't be x. I would even relabel that as theta. Let's start to get used to that. The calculator is going to call it x when we type it in, and we could change y to be f of theta. And you can see that the y-axis isn't scaled. It's got some tick marks, but it's up to us to choose which one we want. And that's kind of what I want to think about with you first. How should we scale this graph if it's just going to be sine of theta? Now you're going to see me drop down here for a second. I want to drop something in the chat that you guys are going to watch on your own. Like stay muted up, because when I share my screen and play a video, it's super choppy. I'd rather you just watch it on your own. It's like literally 30 seconds. I'm down here, I promise. This one, this is what I want. Okay, because we're gonna do sine first. I just wanna show you where this stuff comes from. Us opening up angles. So just watch that really quickly. And I'm gonna talk a little bit while you spend the next 30 seconds or so watching it about kind of what's happening. And remember what we're trying to do when we're opening up angles. We're going to open them up first in the positive direction, right? We're going to start in standard position. We're going to open up an angle in the unit circle, and we're going to track just the y value. Remember, because sine is just y. And so when we start graphing these trig functions, we're only looking at certain parts of the unit circle as we make that trip around. And so if you're watching this video right now, hopefully what you're hearing is that crazy ominous music that I really like. But you're watching the unit circle roll around the x-axis, like roll along. And there's a dot that tracks a point that is the y value at that spot. right? And then it backs up. It starts to back itself up because not only can we open up positive angles, but we can also open up negative angles as well. And what's really nice, and you can just watch the video once and then close it. What's really cool about the way that they track that point is they are like, there's no gaps, there's no breaks. They are plotting every single y value between 0 and 2 pi. And then as they, I guess as they kind of undo that, you can see it kind of, as they kind of track that y value going backwards, and it like erases the curve, that wave that it was going through, it's really opening up the negative angles, and you can see that it just kind of covers itself once again. And so what I want us to do with our graphs here, I don't want to erase everything, let's just erase a couple things, is I want to start just going in the positive direction first, and then we'll start opening up angles in the negative direction, but we are not going to plot every point. We're not. We're going to plot probably more than we need to just this first time around, just so you can kind of get the hang of graphing these one by one. But then as we get further into this, maybe later today or certainly tomorrow when we start messing around with these graphs, we really only need 5 points. And then we'll just connect them nice and smooth once you get the hang of what these curves are going to look like in that kind of trigonometric wave, which is super cool. So you can see that my graph has 0 and then pi over 2, pi, 3 pi over 2, and 2 pi, but it has the spaces in between as well. So it's like 0, 90, but also the space in between, like halfway, so that 45, that pi over 4 spot. We'll graph that as well. We could, if we wanted to, we could graph the pi over 6s and the pi over 3s, all of those multiples of 30 and 60, and get a really, really, really accurate graph. And we're going to do that early on, but the further along we go, the less points we're going to graph. But I want to do it really, really carefully with you as we go through this to start. So take out any color you like, it doesn't matter. And it can just be a pencil, that's cool. And I just want to plot some points. And because we're going to graph sine of theta, we just care about the y values along the way, okay? So if you have your unit circle out, it makes it really, really easy, so you don't have to try to recall the y values the whole way through. But the thing about the unit circle is there are some irrational numbers, right? If I stop at 45 degrees or I stop at 30 or 60, we might run into some spots where we have some y values that we might not know exactly what those decimals are, and that's what I want to remind you of first. There are really only 2 irrational spots along the unit circle, and that's radical 2 over 2 and radical 3 over 2, and knowing those decimal approximations can be really helpful when we're doing these graphs, okay? Radical 2 over 2 is approximately 0.707. Blah, 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 blah. Obviously, that's going right there. So we'll use that decimal approximation to help us plot some points. And then radical 3 over 2 is approximately 0.866. Having those two in the back of your mind can make this a whole lot easier. And when I go through this and I plot all these points, I want to keep these in mind, but we also have to think about a scale that's going to work. And so think about the y values in the unit circle. And since we're just graphing sine, I just really care about what range these y values are going to fall between. Like what's the biggest y value and what's the smallest y value? Well, the unit circle just has a radius of 1, right? And so it can only go up to 1 and down to -1. And so that's the only vertical space that I'm going to need when graphing plain old sine of theta. And so when I think about scaling my y-axis, yeah, sine is y, cosine is x. Well, I don't care if we're graphing sine or cosine. The y values, f of thetas, right? My y values are either going to be the y values from sine or the x values from cosine. So that part doesn't really matter. So either way, my range is going to be -1 to 1, or my range is going to be -1 to 1 sine or cosine. So let's use that as our space. Let's maximize how far up and down we're going by making like 1, 2, 3 all the way at the top here. I'm going to switch colors. Like let's make that 1 way at the top there, and way down here at the bottom, let's make that -1. And let's break these 4 tick marks up into quarters that way, making this like 0.25, making this 0.5, making this 0.75, negative 0.25, negative 0.5, and negative 0.7. Okay. You probably don't even need to write in the scale, but first time around, it's nice to do that. But that's a really nice scale to use when we're looking at just plain old parent functions, just sine, just cosine, not 3 sine of theta or sine of theta plus 7 or something like that. A scale like this should do just fine for us. Cool. All right, now let's actually plot some points and get after it. Okay, and so what I'm gonna hope you can follow along with me. I'm not going to pull up my unit circle. You're going to have yours out. I'm going to go rather quickly, and we're just going to name the y values at each of the points along the unit circle, including the 30s and the 60s. Obviously, we're not going to tick mark those as we go. We're just going to estimate those locations. Between 0 and 45, 30 is about exactly 2/3 of the way through. But let's start at 0. Let's open up positive angles. So we're going to start in standard position. We're going to go up from there, and we're going to go this way until we get to the end. And then we'll go backwards. Then we'll go start in standard position and go down and see what happens. Okay, so y values only as we work our way around. I'm not going to ask you for them. We're just going to go quick. Okay, when we are at 0 radians, the y value is 0. So I'll put a point at 0, 0. Okay. Now, 2/3 of the way into that first box is where 30 degrees, where pi over 6 is going to be. And just this time around, when we do sine and we do cosine, just the parent functions, we're going to stop at those spots. From here on out, like after that, we won't. But so 2/3 of the way into that box is going to be pi over 6. When you get to pi over 6, the y value at that spot is 1/2, right? So 0.5. So I've got this point right there. I don't know how well the green is showing up for you guys. You know what I'll do? Let's pick a larger point and let's make it kind of let's go with like a purple. I wonder if that would stand out. There we go. Okay. So my points are obviously exaggerated, but so 2/3 of the way into that first box, pi over 6, 1/2. Okay. Now let's stop at 45 degrees. Let's stop at pi over 4. Now that's at radical 2 over 2. That one, I put a green line through it accidentally, 0.707. So we don't have exactly that spot. So we kind of just have to estimate it so right on that first grid line to the right, but underneath 0.75. Not going to be perfect, but kind of close, right? 0.707 is relatively close to 0.75, so something like that. Let's stop again at 60 degrees. Let's stop at pi over 6. Which is going to be 1/3 of the way into that next box. So do your best to estimate that spot. But that's at radical 3 over 2, right? The y value at pi over 3 is radical 3 over 2. So 0.866, that's halfway-ish between 0.75 and 1. There's a lot of estimating going on here. So 1/3 of the way into that second box and about halfway up, we get to right about there. There's about 0.866, something like that. Okay, and then we finally get to the top, pi over 2, the y value. And what you can see is though it kind of looked linear to start, like we were just kind of heading up, it does start to flatten out. And I don't know if you noticed this when we were first watching that video, the way the unit circle rolled along the x-axis happened really fast at first, but then it started to slow down. Because the y values start to slow down in the way that they change, right? As you make your way along that circle, it kind of flattens out towards the top, and then it starts to come back down. All right, let's stop at 2 pi over 3. And so let's stop at that 120 degrees. Well, that's the exact same y value as the one right before it. And so wherever your estimation was for that 0.866, go straight across. Well, don't actually draw it though. Go straight across and about 1/3 of the way into that box. Or 2/3, or 2/3 of the way into that box, right? Because we want it to be reflective. Let me back that up. Sorry. 2/3 of the way into the box, because we're looking at a bigger circle, right? A bigger wedge. Go straight across and put a point. okay? Then we get halfway between pi over 2 and pi, which is 3 pi over 4, and that's at that radical 2 over 2 again, but we have an estimation for that, right? We've got a spot. So wherever you did your estimate, it's not going to be perfect, but we want to be consistent. And so wherever your 0.707s and your 0.866s land for you, when you find another spot that's exactly the same, just go straight across and put a point in that spot. Cool. All right, now we get to that 150-degree spot, that 5 pi over 6, and that's at 1/2 again. So we go 1/3 of the way into that next box. You can see why we're not going to do all this estimating as we go through it again, but I wanted you to have one really, really good one. And we get to there, and then finally we get back down to the bottom, and the y value is 0. And there's that, it looks almost parabolic, right? It looks kind of like an upside down parabola so far. But now that we're going to start coming down and we're going to curve our way back, right? Our y values are going to dip down to -1, but head back, that's what's going to create the wave for us. So let's kind of continue what we've been doing, but now we dip into the negatives. So when we get to that next spot, when we get to that 7 pi over 6, we've got that 1/2 again, right? The y value at that spot is 1/2. So I go to that -1/2 spot. 7 pi over 6 is going to be 2/3 of the way into that next box. So I put a point right about there. It doesn't have to be perfect. Do the best you can. Cool. Then we get to 5 pi over 4. We're at that 0.707, but in the negative. So I'm down here. And I'm just trying to match about how close I got to the 0.75 from the top as I do in the negatives. The better you estimate, the nicer these are going to look. Okay, cool. Let's keep going. Let's get to that 0.866 spot. So we're going to go 1/3 of the way into this next box and the negative 0.866. So like halfway-ish between -0.75 and -1. And then 3 pi over 2, we're finally at the bottom of this graph, and we put a point right there. And if you notice what happened on the top half, where we just went straight across and just kind of reflected this over, now we can do that again. I know that, okay, I was 2/3 of the way to this point, so I'm going to just kind of match that over here. I'm going to use that 3 pi over 2 line. It's kind of an axis of symmetry, and I'm just going to reflect that over and match, and match, and match my way back. And if you use these reflective properties, man, this stuff gets so much easier because you really only need a handful of points, and then you can fill out the rest in between there. Cool. And so that was that first trip around the circle, and now you start to see that wave, which is really, really fascinating. Now, let's go back the other way. And all we're going to do is we're going to start at 0 and go down. But what you'll see is that exactly what just happened right here is exactly what's going to repeat itself this way, because it's the same circle just going in the opposite direction. And so we don't have to talk through this quite as much anymore. Now we can almost, in a way, take a copy of this graph and slide it over right to there. And so that's kind of what I'm going to do. I'm going to say, okay, this 2 pi spot, well, that's exactly the same as 0, right? Because it's that starting point. And now I'm just going to copy this over to here using these grid lines as kind of a map for me. All right, my next point from 2 pi, all right, so I got to go to -1/2, and it's got to be kind of close to the next one. And then my next one was that 0.707, but in the negative, and it was right on the line. And then the 0.866 was like right here, and then the -1, and the negative 0.866. And I just kind of copied this over as best I can, making sure that I get a really nice version as close as I can to what I just had. And I just keep going, okay? And I could slowly walk you through this, or we could speed this process up and start estimating our way to a lot of really nice points. Obviously, my points are much bigger than yours, probably because I'm using that big, the size of my marker, right, is the medium one here. So, and there we go. Nice. Now, we left out 1 degrees and 2 degrees and 3 degrees and 4 degrees and all the ones in between to make our lives just a little bit easier. And so to fill in those gaps, now we just connect. And I usually just connect it as best I can from left to every time. I gotta turn off the go to sleep button. The idea here is to do this freehand as smoothly as you can, as nicely as you can, as symmetrically as you can, allowing this wave to basically draw itself. Now, these keep going, obviously. So what we should do on the left-hand side, extend it, little arrow, extend it, little arrow. Okay, because these waves do go on forever. And your graph should look something like that. Now, if we chose a different scale, then maybe it would be squished down or stretched out this way. And that's what's going to happen when your calculator, that's what I want to do with you real quick, show you a little bit around the calculator. Where's my present button? There it is. What happens when we try to graph things like sine in your calculator? I'll just do my whole screen. It's just easier. Okay, so if you have your calculator nearby, take a look and do it with me, or at least just watch me here, because I want to show you some of the things that get screwed up when we try to graph things like sine and cosine in the calculator. So I went in already. I'll delete it so that we can start fresh. I just went into y equals, got rid of everything that was there, and there's my trig buttons in my calculator. There's sine, cosine, and tangent. Obviously, they're not going to put cosecant, secant, and cotangent because we can just do like 1 over sine, 1 over cosine. Like here is cotangent, 1 over tangent, right? But we're just doing sine. But look what happens: sine of something, right? It wants us to put something in here. It needs that independent variable because all we've done is picked a trig ratio, right? We haven't made it a function yet until we have an angle to put in. Now, your variable button where you would normally type x doesn't just have x there. It has x, t, theta, and n. There's our theta right there, right? But if we click that button, it's just going to type an x. That's what the calculator likes to do. No big deal. We know that it's theta. Of course, we want to close that parentheses to get us there. And depending on what window you're in, things might look different. I'd like to all kind of start in the same window, maybe a window that you'd be more likely to see to start if you were graphing other stuff before this. Let's go to Zoom, and let's just click Zoom Standard, right? That's kind of the one that we usually start in, so Zoom number 6. And we get a graph that looks like that. Obviously, that graph, sine of theta, in Zoom Standard, for me, does not look like this one. Can anybody figure out why my graph is screwed up? Like, what is it about the calculator's setup right now that's giving me something that just doesn't look right?
It's in degrees instead of radians.
I'm going from -10 degrees to 10 degrees. I'm only looking at a window that's about this big, which is why it's going from like negative, not so much, to positive, not so much, right? We want to make sure that when we're doing this, our mode, so right next to the second button, mode, we got to switch that to degrees, from degrees to radians, right? Now, when I graph this thing, now I start to see that much nicer wave, because now I'm going from -10 radians, which is more than a full trip around the circle, to 10 radians. Remember, 1 radian is not 1 pi radian. A radian is the arc of the circle that matches the length of the radius, right? 1 radian is about this big, right? That gets you to about there. There's more than 6 radians in the unit circle because 2 pi is twice pi, right? So 3.14, double that, 6.28, right? So we're seeing more than 2 full trips around the circle, and this looks a whole lot better, but it's really kind of squished down, right? Because now my y values, I'm still -10 to 10, -10 to 10. And while that might work when we start messing around with the size of the graph, right? We start messing around with amplitude and things like that. I kind of want to see this. That would be nice. I wish I could see something that looked a little bit closer to this. And so you could do that yourself by going to window and changing things yourself, which is fine. Like you can change your x-min to -2 pi, like actually type in -2 and then second caret, right? There's pi right there. Now it's going to estimate it for you to 2 pi. You could do this all by hand. But now I get to this x scale spot and it's still going by 1 radian at a time. Not pi radians or something like that. So you could manually change your x scale as well to be the same scale that you have on this graph, which for us, 1 tick mark, that's what scale is, was pi/4. Okay, and if you press enter, it'll change that to the decimal approximation for pi/4. But hey, at least now, my wave from left to right is those 2 full periods of that trig wave. And these marks along the way, there's pi/2, right? Pi/4, pi/2, there's the max right there. But I'm still super like squished down because my y scale is still -10 to 10. You can change that to -1 to 1 if you wanted. You could manually do all of that stuff. And then your graph will look a whole lot better, right? There's the perfect copy of what we've got. And so if you want to do that, great. If you want to go to window and manually change everything to be multiples of pi or pi/4 or whatever you got, you can do that. But that takes a lot of work, right? That you had to know exactly what to do and what everything meant. There's a much better option. That Zoom choice that we made with Zoom Standard was a terrible first choice when dealing with trig. Look at your Zoom menu. Is there an option that you think might be a better place to start given the fact that we're graphing these trig functions?
Zoom trig.
Number 7, the one right below Zoom Standard. And I think that's why they put it right after it, because Zoom Standard is such a nice one to start with if we were just looking at like polynomial functions or something like that, or even rationals. But Zoom trig right after that, so I'm just going to go down to number 7 just by pressing the number 7. And you can see that it breaks things up a little bit nicer. Now, it's not -1 to 1, but it is this exact same setup in terms of scale, in that there are 4 tick marks going up and down. The thing that I actually do like about what Zoom trig does is it goes a little past -2 pi and a little past 2 pi on the right. It gives us just a little bit more space so we can see that wave continue on and on and on and on. Okay, cool. So there you go. So a lot of cool things that you can do in the calculator to make your graphing life a whole lot easier. Of course, you can go to the table and get some values, but your x's right now are still like 0 radians, 1 radian, 2 radians. You would have to change the way your table is set up so that it goes by the tick marks that you have, in case you wanted that. So maybe you want to start at -2 pi, right? I'm in my table setup, second window. And then my delta table, maybe I want that to go by that pi/4. And you can see that my independent and my dependent are back to being set to automatically giving all the stuff, right? We're not going through that process of like graphing these things by hand like we were doing back in the first semester where we would ask for certain values. Now, when I graph this, right, it still looks like that, but my table gives us those really nice values. And you can see that because we picked pi/4, it's skipping all of the pi/3s and pi/6s, which were kind of tough. And there's the 0.707s in between. All of your 45 degrees, all of your multiples of pi/4, those will all be the 0.707s right there, which are really the only ones that we need. Your 5 points that we care about. The first one, the top, the next one, the bottom, and in between. Those are going to be the 5 most important points. If you want the 0.707s in between, usually what that does is just kind of give you a guide to make sure that you're not going down too fast or up too fast or down too slow or up too slow, because it's really easy to make the mistake if you just have that red dot to go like that. To kind of get to that point really quickly, crossing at pi/4 a little bit too low. So although 5 points is really kind of the minimum, I like to do the ones in between. I like to have the 1, 2, 3, 4, 5, 6, 7, 8. I like to do 9. Okay, I like to have those 0.707s in between the pi over 4. Cool. So there you go. Nice. All right, that took forever. Let's speed this process up. Let's do another one. Let's do cosine. I'm gonna clear this out, but first, questions? Most of us, if not all of us, have seen this before from last year. I'm hoping that sine graphs, by the way, the name of these kind of graphs, this might be like it's like top 5 math word of all time for me. These kind of graphs are called sinusoids. That's just so much fun to say. Sinusoids, graphs that look like sine. Okay, sine waves. Okay, sinusoids. Awesome. All right, so that was graph number 1. If you have a copy from me, let's go down to graph number 2. I'm going to clear this whole thing out. And we're not going to do the pi over 3s and the pi over 6s and stuff like that, but we are going to stop at all those pi over 4s. So this is graph number 2 for me. And let's call it like g of theta. Let's mix it up, and let's do cosine. Okay, if you want, you don't have to. You can rename the y-axis g of theta. You can rename the x-axis theta. Not a big deal. I'm not going to stress about it. But I do want to give you a kind of a slightly less interesting. I don't know. I kind of like the first video a little bit better, but I want to show you the cosine video. Again, it's just like this little half hour, 30-second, half a minute clip. About where the cosine one comes from. It's just not quite as fascinating, but I still want to show it to you. But I bet you know what it's going to look like. It's going to be that unit circle. Go ahead and click on that if you'd like. It's going to be that unit circle rolling along the x-axis in the positive direction. But this one's a little bit harder to watch because the point was really easy when it was just the y value. We just followed the point along the unit circle and watched it go up and down, and it just matched that. This one is going to do the same thing. It's going to have that point, and we're going to open it up along the circle and see what happens. But the output is the x value along the way. And so you're going to see this blue spot. You're going to see this blue line that's measuring the x distance at that point as we open up that angle on the circle. And the output, the blue graph, I think it's blue, the blue graph that goes through is the x distance from 0. Because remember, we're just looking at the unit circle, making our way around. And as we open up that positive angle, we're going to track this point. But the part that we care about is how far away it is from the origin. Okay, so it's a little bit trickier to see, but what you'll notice is that that's exactly what it's doing. Okay, it's going to track how far away we are from the origin. And let's do the same scale. I'm just going to put a 1 at the top here and a -1 at the bottom. So here I am on graph number 2. I'm not going to put all those scales in between. We now know what they are. Obviously, if 4 boxes is worth 1, then every box is worth 1/4. And we'll just mark points at these nice tick marks now. We're not going to do the 30s and 60s. For the x coordinate at different radian measures along the unit circle. We'll start at 0 and go positive. We'll start at 0 and then go negative. And they'll just copy one another. Okay? Cool. Let's do it. I'm going to go red this time. And if you have a unit circle, this gets really easy. Okay? Sine started in the middle, right? Started at 0, went up, down, and then came back. Sine starts in the middle. Cosine, because the x value at 0 degrees is 1, cosine actually starts at its maximum. Okay, cosine begins at its maximum and then goes down from there. And when we start getting really a little bit more in-depth kind of stuff, knowing that cosine begins at its maximum, I think it's so important. I'm going to write it down. Cosine starts at its maximum. That's going to be a lot easier when we're given a graph and they're asking us to find the equation, a cosine equation for that function. We're just going to start at a maximum value. We're just going to look at a graph and say, hey, ooh, there's the top. That's where cosine starts, especially when we start sliding this stuff left and right. Cool. All right. So there's cosine 0 radians. The x value is 1. Then we get to our 0.707 at pi over 4. That's always going to happen because the x and the y value are the same there. So 0.707 was right about there, right? Kind of close to the 0.75 spot, a little closer to that than the 0.5. So maybe just something like that. And then at pi over 2, x is 0. And then negative 0.707. And then we get to pi, we're down at negative 1. Because that's the x value at 180 degrees. And then back up we go, negative 0.707, 0, 0.707, and then 1. Now that almost looks parabolic, except kind of at the end, it starts to hook back a little bit, which is why I chose a graph that looks at 2 full cycles of these sinusoids rather than just one, because trying to graph one cycle of this can be kind of tricky unless you know to like really arc down from the maximum slowly. It kind of has this arc motion there. I like to do 2 full cycles any chance I get, or at least just something more than one, because it'll give me a better feeling when I'm trying to trace these graphs myself. So let's take this whole thing and let's go into the negative, which really just copies it over. Because these waves are periodic, they're just going to repeat, repeat, repeat. There's a lot of periodic motion. The phases of the moon, the clock, time is periodic. Something starts, goes through its process, and then restarts. Your sleep cycles, all that kind of stuff. Okay, so I'm just going to take this and copy it this way. But really all I'm doing is I'm opening up an angle down. That's my negative angle, 0.707, 0, negative 0.707. So I'm just on the grid lines now, no more in-betweens going left and right. Negative 0.707, 0, 0.707, and 1. And now I see that wave a little bit better than I did before. And now I disconnect it. Now we just connect it. Right? So you've got this, and I'm going to do something right here so you can see it. You don't have to do this with me right now, but the points that I happened to connect, that's just a sine wave, right? So sine and cosine, they're the same wave. It's just shifted over a little bit. Now, when I connect all of them, right, that's what's going to make our nice cosine wave, but really they're the same. And so when I called the first wave a sinusoid, so is this one. Both sine and cosine. This is a sinusoid as well, because they are the same looking graph. Obviously, one is a sine graph, the other one is a cosine graph, but they're just phase shifts of one another. Now you don't have to do this, but I'm gonna put sine just on this graph so you can see it real quick. I'm just gonna do that and then copy it over. You can see how fast you can get. You can do it if you want. I'm just going to do it real quick. Like there's sine on the same graph. They're the same. They're just shifted over a little bit. Okay. And there's the basics of graphing sinusoids. Okay. It's 9, 10. That's good. Let's stop right there. It'll give you a couple minutes in between before your next class gets going. Sine and cosine graphs, okay, all of your sinusoids. That's the start of 4.5. Okay, so if you wanted to give this thing a title, you can call it 4.5. What we'll do tomorrow is I'll dive into the equations that go along with these and all the transformations that happen. Okay, so if you want to peek ahead or if you want to think back to what you might have done last year with amplitude, period, phase shift, vertical shifts, midlines, and things like that, that's what's coming tomorrow. But nothing you need to do between now and then. Just come back and see me one more time. And then probably Friday, I'll have some things for you to practice with and call that like our first homework. Okay, but more on that as it comes. Before I let you go, I put an announcement on Canvas for See You Succeed, for College of Trig stuff, with all the important links and dates and tuition and all that stuff that goes with it. So you can get signed up if you're interested in signing up for the class. Totally up to you. Of course, it's optional, but you will be well prepared when we get to that process in May to take that final. I promise. If you felt pretty good about your college algebra, college trig should go just as well. We'll do everything we can to get you ready. If you need your student ID number, just shoot me a message and I'll send that to you individually. That's not something I want to share out. That's privacy stuff. So let me know if you need your old CU student ID to get registered. And I will see you tomorrow. Let me know if you have any questions. Otherwise, thanks for hanging out. Have a good day. Bye, guys.
Thank you.